All right, welcome to chapter 23, where we'll be talking about the chemistry of amines. This should be a topic that you're at least a little bit familiar with by this point in the semester. We've been using amines for various transformations, and they've been showing up here and there. In this chapter, we'll discuss their chemistries in a little bit more depth. So by the end of today's lecture, you should be able to explain how different substituents on an amine affect its basicity. You should be able to predict the more basic amine in a pair of amines, or the most basic nitrogen in a molecule with multiple nitrogen atoms. You should be able to draw a mechanism for the formation of alkyl azides and predict the product of their reaction with lithium aluminum hydride. We'll talk about what an azide is and what makes them special. You should be able to draw a mechanism for the Staudinger reduction and the azavidig reaction. We'll cover these toward the end. And then finally, you should be able to use these above reactions in multi-step syntheses. And what this last point basically means is you should feel comfortable with the types of products you can form from them. And if given a product, you should be able to say what starting material it came from given conditions. So this is a matter of familiarity, and I hope that by the end of this video, you're a little bit more comfortable with some of these reactions. Before we start with reactivity, it's a good idea to talk a little bit about nomenclature because there are a couple points of confusion with amines. In the top left here, we have just a generic amine where these R groups are carbon, silicon, hydrogen, and so forth. They are not carbonyls, nitrogen, or oxygen. It's not R groups. If they have those sorts of R groups, they're something totally different. We'll talk about what those are here in a second. An example of just a generic amine is something like triethylamine here, shown at the bottom. This is a generic amine used as a relatively non-nucleophilic base. Another subclass of amines are called amides. You may see these two highlighted examples in the top middle and top right. This is tremendously confusing, the differences in how you say them. So with this red example in the middle, amides are nitrogen anions that have no resonance stabilization or no electron withdrawing resonance stabilization. So an example of this would be sodium amide here. And you pronounce that using this pronunciation key here, amide. And those are different than amides, despite the fact amides are spelled much the same. Old school organic chemists are doing us no favor with this nomenclatures, but this is what it is. And so amides, pronounced amide, are nitrogens attached to a carbonyl. And indeed, we've seen these before. I hope that this is familiar. An example of which is called acetamide, or acetamide here, sorry. Acetamide is this molecule here. And it is one of the more simple amides. All right, these bottom three are not necessarily considered amines, but their chemistry is closely related to it. So, are considered amines, but are a subclass of amines. So anilines are nitrogens next to an aromatic ring. We'll talk about what an aromatic ring is in a couple chapters, chapter 20, but anilines have something like a phenyl group attached to them. This changes their properties substantially. Notably, anilines are some of the earliest examples of organic dyes, and in fact is one of the earliest applications of organic chemistry dating back all the way to the 1800s. I have one example of an aniline stain here, an aniline dye, and they have beautiful colors. And this is due to the conjugation that they have with the phenyl groups next door. Another type of amine subclass are what's called pyridines. These are nitrogen benzenes, where there's a nitrogen in the benzene ring. These behave as weak bases, and we'll talk about their conjugate acid's acidity here in the next slide, well, 2 slides from now. And then finally are a subclass of molecule called ammoniums. And this molecule we have here, they are nitrogen cations. Tetramethyl ammonium is the one in the bottom here. There are other subclasses of amines, but these ones will get you pretty far. There is one that is not listed on this slide called an azide, and that's because we're going to talk about it toward the end. And so what you should know from the slide is you should know the general classes of amines. That is, I'm not a big fan of nomenclature. However, it is very useful when interpreting what I'm saying in class and interpreting problem questions and so forth. So you'll never be asked to just draw one spontaneously given a word. However, this is well worth your time to study and learn this nomenclature. So what is the structure of amines and what makes them unique and different than, say, carbon? Well, the biggest structural component of an amine is the lone pair when it's in its neutral state. So here we have a molecule that is ethylmethylamine. It has a methyl and an ethyl off of it. And what's interesting about these is you can draw them as a chiral molecule. That is just like carbon. If carbon had 4 different substituents off of it, we would have 1, 2, 3, 4 different substituents off of our nitrogen. However, nitrogen lone pairs do what's called inversion. It's sort of like an umbrella flipping upside down. And what this does is it inverts the stereochemistry between the R and S enantiomer, as we can see here. The net effect of this is that this occurs at room temperature. So the net effect is that this is not a chiral center because we can't isolate a pure S or R tertiary amine or something like this, okay, where there is the lone pair. These are not configurationally stable is what we say. That means that they flip back and forth between their 2 enantiomers, and so there's really no point in assigning it a stereoisomer because it is almost always a racemic mixture. Now, this is not true of ammoniums. Ammoniums do not have this lone pair. Ammoniums, again, are these nitrogen cations, such as this one shown here, and they can indeed be chiral. Because they don't have the lone pair that does this sort of umbrella inversion, they are configurationally stable. And then finally, the last property of amines that we're going to want to talk about are hydrogen bond donor and acceptor character. Amines with a hydrogen coming off of them can be hydrogen bond donors or acceptors. Amines with 3 alkyl groups with no hydrogens off of them can be hydrogen bond acceptors. So one of the most important properties of amines in human physiology and just in general is their basicity. Amines have a lone pair that can be protonated. So here we have them in their base forms. Their conjugate acid forms are the ones drawn in red here. All right, and so the basicity of these is related to the pKa of their conjugate acid. Sometimes the pKa of something's conjugate acid is called a pKaH. So the pKa of ammonium is 9.2. Of ammonia is 38. And of this NH2 here, it is so basic we can't make it. It doesn't exist, so it doesn't even really make sense to talk about. We can't form a nitrogen dianion. Not readily, at least. So we don't even talk about its pKa. You can imagine if ammonia's pKa is 38, or the pKa of amide is 38, you can imagine that deprotonating it twice would make it much, much higher. And we don't have much room beyond 38. Once we get into pKa's of the 50s, we've kind of run out of space. There's nothing that can deprotonate things that are that basic. So the conclusion from this first series we're looking at here is that basicity increases with increased negative charge. That is, amide is a strong base. Its conjugate acid has a pKa of 38. Ammonia is a modest base. Its conjugate acid has a pKa of 9.2 in water to generate ammonium. Ammonium has a pKa of 9.2. The second thing that determines amine basicity is resonance stabilization. So resonance stabilization stabilizes the lone pair, and this makes them less willing to be protonated. So the conjugate acid of this molecule here, diphenylamine, has a pKa of 0.78. The conjugate acid of aniline, anilinium, has a pKa of 4.6. And then finally, cyclohexylamine, which has no resonance. This is in contrast to aniline and diphenylamine. These do have resonance structures where these lone pair can resonate into the ring, and this stabilizes them. Cyclohexylamine does not have that. And its pKa is 5 orders of magnitude higher than aniline's. Nearly 11 orders of magnitude higher than diphenylamine. So the conclusion here is that resonance stabilizes lone pairs, and this makes them less ready to be protonated, okay? So that is the second factor affecting amine basicity. The third factor is that electron withdrawing groups decrease amine basicity. This is highly consistent with what we've already talked about and should feel intuitive at this point. If not, review the cardio lecture from the beginning of class. But here we have an electronegative oxygen atom. This electronegative oxygen atom, highlighted in blue, is highly electronegative, and it will withdraw electrons. It's electron hungry and kind of yanks them towards it. The net effect is that this amine has a lone pair that is lower in energy. They're getting pulled toward the oxygen, so they're less willing to form a bond with a proton. In contrast, piperidine has a carbon at the same position, that is up here. And piperidine has a much higher pKa of 10.9. And while 2.5 or so pKa units may not seem like much, this is between 100 and 500 times more basic. That's a lot. So these small changes can have profound effects on the molecule's properties. Piperidine is about 500 times more basic than morpholin with just this oxygen atom. This also applies to other types of amines. Here we have the benzene derivative, the phenyl derivative of nitrogen called pyridine. And if we put an electron withdrawing group off of that pyridine, that is chlorine, chlorine is electronegative, an EWG, it pulls electrons towards it. This has the same effect as oxygen in morpholin. This makes it much less basic. In fact, it moves the pKa of its conjugate acid being 2-chloropyridinium, this is a pKa of 0.49, which is many, many times more or less basic than pyridine. Another way of saying that is many times more acidic than pyridinium. So the last section we're going to talk about is the effect of hybridization. Indeed, this is very, very similar to hybridization of carbon. We talked about sp versus sp2 versus sp3 hybridization in the context of organolithium basicity. If you don't recall that, please take a look at it. But what you need to know is that sp orbitals are generally more acidic. That means that their deprotonated forms are least basic. Those are one and the same way of saying the same thing. So here, the orbital on this nitrogen is sp. The orbital on pyridine here is sp2. The orbital on piperidine, this molecule on the right, is sp3. And the basicity trends go this way, where the sp3 is most basic. Now, it is really important that you're able to assign the hybridization of these orbitals. So if you cannot assign the hybridization of these orbitals, please review the hybridization that we discussed early in the semester during review week. This is incredibly important, and you should be able to identify it quickly. All right, so let's apply what we just learned to identify the most basic amine in each triplet here, each group of 3. So let's start in the top left. Here we have dimethyl-aniline, molecule A. We have trimethylamine, molecule B. And we have dimethylacetamide, compound C. Now, what we just learned up top is that resonance lowers basicity, that inductive withdrawing effects lowers basicity. And so C has resonance. Remember, the most basic spot of an amide, like this, is the oxygen. And this resonance structure tells us that. And remember here that these lone pairs can also resonate. They can resonate into the phenyl group. And so here the strongest base is the amine that has no resonance and no induction. And I'm going to say that as EWG. EWG means electron withdrawing group, highlighted in blue. So the most basic amine in this case is amine B. Let's move on to the next group. We have pyridine, we have 4-fluoropyridine, and we have 4-chloropyridine. And the only differences amongst these compounds is that each pyridine has either nothing at all, a hydrogen at the 4 position, or a fluorine or a chlorine. And so the most basic amongst these is actually compound D. Compound D does not have electron withdrawing groups. Again, electron withdrawing groups reduce basicity. Another way of saying that is they increase acidity of the conjugate acid. Ca, and Ca in this case will mean conjugate acid. Now let's move on to this final grouping of amines. We'll call this this trimethylamine, in this case X, Y, and Z. And so these amines are actually quite similar. They're all nitrogen, that is sp3 hybridized, that is there's no resonance, none of them have resonance. However, one of them has a bunch of fluorine atoms off of it. And so compound Z stands out, and fluorines are electron withdrawing. And remember from up here, highlighted in blue, electron withdrawing groups reduce basicity, or they increase acidity of the conjugate acid. In this case, we have a ton of fluorines off of our amine. These are electron withdrawing groups. Fluorine is electronegative. This amine is certainly the least basic. In fact, this molecule is called perfluorotributylamine, and this is an artificial blood substitute. It solubilizes oxygen very well and can be directly injected into people's blood veins to help them when they're having hypoxia. Now, our question here is now between X and Y. Compound Z, again, has electron withdrawing groups, and this reduces basicity. So the most basic compound between X and Y is actually compound Y. And this is because alkyl groups are saturated hydrocarbons. In this case, this is tripropylamine. Alkyl groups are seen as slight electron donors. So if electron withdrawing groups reduce basicity, electron donors increase it. And alkyl groups are considered weak electron donors. The pKa of X and Y's conjugate acid will be similar, but Y is almost assuredly more basic. So moving on to an example where we have 2 in 1 amine. In this case, our molecule of interest is procaine. Many of you may have had procaine injected into your mouth when you're at the dentist's office. It's a local anesthetic, very simple one at that. Procaine has 2 different nitrogens, highlighted in green and in blue here. And we're trying to determine the most basic nitrogen on these. And so if we compare them, the thing that should stand out is that green nitrogens, lone pairs, can resonate into this ring. And not only that, they can resonate all the way up on this oxygen to make a resonance structure as such. And what this tells us is that these electrons are stabilized. Resonance stabilizes compounds. And when they're stabilized, that means they're less reactive. So since they're less reactive, they are less basic. Indeed, the most basic nitrogen on this molecule is this amine over here, which has no resonance stabilization and very few electron withdrawing groups. This oxygen is an electron withdrawing group, but it has a much smaller effect than the resonance over here. So the most basic amine on procaine is the alkylamine over here on the far right, circled in green. And that is because of the resonance stabilization of the nitrogen over here. And this is actually an aniline nitrogen. Now we'll just write res stabilized. All right. So moving on, what are some of the most important synthetic methods for the preparation of amines? Well, amines, the most common thing bonded to nitrogen, other than hydrogen, is carbon. And so if we want to make an amine that is attached to carbon, say from ammonia, one way of doing so is through alkylation. Here we have ethyl iodide. And what we'll find is that this is actually very difficult to control. And the reason for that is that the product amine, ethylamine might have been what we were shooting for, is more nucleophilic than the starting material. So ethylamine will undergo further reactivity to make diethylamine or triethylamine or tetraethylamine, ammonium. So alkylation, while a possibility, is difficult to control unless we're trying to synthesize ammoniums, this product here, because then we can just add excess ethyl iodide and all the product will eventually funnel to this tetraalkyl ammonium. So this is not a very good strategy. Another strategy that we've actually already learned is what's called reductive amination. And in this reaction, as its name would imply, it's a reduction and it proceeds through a key iminium intermediate. Iminium looks something like this. And again, our R groups could be anything. It goes through this ammonium intermediate and a hydride gets added to the iminium ion. This is reductive amination, and this is indeed highly controlled, but due to the reagents is not always compatible with the synthetic method. Now there's another method that is highly selective for the synthesis of amines. However, it comes with some other nasty side, or it comes with another set of problems. And that other synthesis is via azides. So an azide is the N3 anion shown up here in the top right. And the resonance structure of the N3 anion is as follows. Second, I have to pause. It's not working. All right, as I was saying, azides are these compounds in the top right, and their key resonance structure is as follows. And this is a failure of resonance theory to adequately describe the structure of azide, and that we have an unusual situation. All octets are filled. It is overall a monoanion. You may see a plus and a minus, but one of the plus cancels out the minus. And these azide can behave as a nucleophile. And so in the context of amination, what this looks like is our azide anion, drawn over on the right here, can react with an electrophile. In this case, we'll use our trusty ethyl iodide. I'll draw it out. Our anion can react through an SN2 pathway to yield ethyl azide. Ethyl azide is a neutral molecule. The plus and minus charge of the two nitrogens cancel out. And indeed, it stops. It does not react further. With electrophiles. Okay, this is important, no reaction. However, alkyl azides themselves are not very useful. They are highly toxic and prone to explosion, as sodium azide is itself. The most useful reactions of azides are their reduction using lithium aluminum hydride to the corresponding amine. Now, this is a two-step process. We have to alkylate first. However, it is highly selective for the primary amine after acidification. So just AQ workup. All right, so lithium aluminum hydride is an effective reductant for alkyl azides. This is a two-step sequence that leads to the selective formation of primary amines. It cannot be used to synthesize secondary amines. Okay. Alkyl azides have another reaction that is called the Staudinger reduction. And so one thing I'd like to highlight is this key resonance structure that we just saw highlighted in green. This key resonance structure of azides is actually somewhat of a failure of resonance theory. Resonance theory, again, is a useful heuristic to help us understand complex situations in bonding, but it is not always perfect. A prediction from resonance theory would be that the middle nitrogen of the highlighted green azide, with a yellow asterisk to it next to it, you would expect the yellow nitrogen to be electrophilic, and if anything, the anionic nitrogen at the end to be nucleophilic. Indeed, this is not the case. Resonance structures or resonance theory fails us. In this reaction, it proceeds via nitrogen attack of our phosphine as the nucleophile, and our azide is the electrophile, to form what's called a phosphazide. The phosphazide then evolves N2 to generate what's called an aminophosphorane. So I'm going to draw this reaction out in full detail so we can see it. Again, it initiates with our phosphine attacking what would appear to be the nucleophilic nitrogen. And again, there's no great explanation for this. This is a failure of resonance theory. There are other ones, but it gets us pretty far. Don't assume that resonance theory is going to fail us. This gets us to the phosphazide. And I'm going to draw it in a slightly different geometry than what's up there. The reason for that, we have a phosphonium cation. We have formally a nitrogen anion here. And what that nitrogen can do is it can attack our phosphonium. Remember, phosphorus doesn't play by the same rules as boron, carbon, nitrogen, oxygen, and fluorine. It is allowed to have more than 4 bonds to it. Its octet rule can be broken. And what that leads to is a 4-membered intermediate as such. And what this can do is it can evolve nitrogen. This is very similar to the Wittig reaction. All right. And that leads to our aminophosphorane. And it ejects N2 in the process. Note that any reaction that generates dinitrogen is generally very, very favorable. Nitrogen is an incredibly stable molecule. It's one of the most stable molecules that we'll talk about in this class. And so this is a tremendous driving force to push this reaction forward. You may say, oh, I don't want to form a 4-membered ring in my mechanism. Well, forming a 4-membered ring leads to evolution of nitrogen. So this is one of the things that pushes it along. Now, what's important about this reaction is that aminophosphoranes, azailids, can decompose in the presence of water to form an amine. We're not going to go through this mechanism, but you should know that these are what's called hydrolytically unstable. Okay, and this affords the amine. So treatment of an alkyl azide with phosphorus will lead to an aminophosphorane, and treatment of an aminophosphorane with water leads to a primary amine. So this is a selective reduction that does not use lithium aluminum hydride. It's called the Staudinger reaction or Staudinger reduction. It is a highly effective means of converting alkyl azides into primary amines. Now, these azailids, aminophosphoranes, have another reaction that they can do very well, and they can actually do the same chemistry as a Wittig reaction. So recall, this is from chapter 16, and you should know the mechanism of Wittig reagent formation and its reactivity. Recall that when we have these phosphorus ilids, like this one here, we can draw them as this resonance structure or a different one, where we see a little bit more about their reactivity. And the key thing about these phosphorus ilids is that they react with ketones. In this case, we'll do acetaldehyde to form alkenes and the corresponding phosphine oxide. So I'll highlight where these compounds are coming from. The green are these two here, and then the fuchsia is the carbon up here. All right. And so this is the Wittig reaction. It turns out that this also works with azailids. When we see aza is sort of a moniker for nitrogen variants of something common. And so the aza-Wittig reaction proceeds through the same mechanism. and it forms what's called an imine. So this is an effective synthesis of an imine, and in this case, Z equals O. All right. And so I'll draw out this reaction. We'll separate it from the normal Wittig. The azavitic proceeds as such. And again, this is identical to the mechanism of the Wittig reaction. The driving force for this reaction is not evolution of N2 as it was in the Staudinger reaction. It is in fact the formation of a phosphorus-oxygen bond. Phosphorus-oxygen bonds are quite strong, and so it is willing to exchange its phosphorus-nitrogen bond for a phosphorus-oxygen bond. Generating our imine. And the corresponding phosphine oxide. All right, so that wraps up the video lecture for today. You should be comfortable with this mechanism at the end here and the synthetic applications of the aza-Wittig reaction, as well as the Staudinger reaction.